right, let's review some important points now. For conservation of energy, the total energy of a system can change only by amounts of energy that are transferred to or from the system. If a system is isolated from its environment, then the total energy of an isolated system cannot change. So in a situation where there are no external forces that do work and there are no non-conservative forces, then we can apply the conservation of mechanical energy, and we have delta K plus delta U equals 0. So remember, mechanical energy is kinetic plus potential. So we can use this principle to solve many motion problems. If there's no friction, we only need to, or if there is friction, we only need to add the increase of thermal energy term, which is the positive value of the work done by friction. And if there are external forces that do work, then we add the appropriate term to account for that. All right, so our summary in mathematical form now. So if we have external forces that do work, then the work done by the applied force equals the change in mechanical energy of our system, which is delta K plus delta U. If we have friction involved, and there's no external forces, then we have delta K plus delta U plus delta E thermal equals 0. And if we have an external force, then the work done by the applied force equals delta K plus delta U plus delta E thermal, where delta E thermal is the frictional force times the distance over which the friction acts. So that's our increase in thermal energy. All right, so we can greatly simplify complicated motion problems. We only have to worry about the beginning point and the end point. We don't have to worry about what goes on in between, except of course when there is friction, we need to know where the friction acts. But again, that's a very simple term. We just take the frictional force times the distance over which it acts. So this greatly simplifies many motion problems. All right, let's look at an example here. The figure to the right shows a ball of mass m attached to a very light string. The ball is pulled back so the string makes an angle of 30 degrees with the vertical, and then we give it a push so it has an initial velocity. What is the least value of the initial velocity v0 can have so that the ball will swing down and then up to a horizontal position? And then part B, we want to push it hard enough so that it will swing all the way around up to a vertical position with the string remaining straight. All right, so let's do part A first. All right, so we're going to use the conservation of mechanical energy. There's no friction involved here, so our mechanical energy will be conserved. So we're giving it an initial kinetic energy. It's going to swing down to the bottom and then up to the horizontal position and then momentarily stop. So the change in the kinetic energy then is just our final kinetic energy, 0, minus our initial kinetic energy, 1/2 mv0 squared. The gravitational potential energy will increase. So rather than counting all the way to the bottom, we just want to find the increase in height from the initial position up to where it is horizontal. So if I draw a horizontal line from the ball in its initial position over to the vertical, and we see we have a right triangle with L as the hypotenuse, and then the height will be equal to L cosine of 30 degrees. So the gravitational potential energy will increase by mg L cosine 30. So the kinetic energy decreases by negative 1/2 mv0 squared, and the gravitational potential energy increases by mg L cosine 30. So then we solve for v0, and then so we multiply through by 2, divide the m out, and then take the square root, and we get v0 equals the square root of 2gl cosine 30 degrees. So if we're given the length of the string and we were given the angle, then we got the initial velocity that we need to get it to swing up to its horizontal. All right, now we're going to do part B. All right, let's do part B now.
We want to give the ball an initial velocity that's great enough so the ball to swing up and make the top of the circle with the string remaining straight. So notice that we can't just set the kinetic energy equal to 0 at the top there, because if the ball only has enough velocity for it to stop at the top, the string will go slack and the ball will fall long before it gets to the top of the circle. So this ball has to have enough speed to make a complete vertical circle for the string to remain straight at the top. So we did this before in the video on centripetal forces where we did the vertical circle, and I'll put a link at the top here for you to see that in case you don't remember. So at the bottom diagram here, I have the ball at the top of the circle with a free body diagram. So the forces acting on the ball when it's at the top of the circle is we have the weight mg down and the tension force pulling the ball into the circle, and our acceleration is down toward the center of the circle. So the bottom left here, we have the equations for that. This is just Newton's second law again. Sum of the forces equals ma. So we have the tension down, mg down, and that equals m times the centripetal acceleration, v squared over L. Now the minimum speed at the top is just when the tension goes to 0. That's the minimum speed to make it through the circle. Then with the tension 0, we have mg equals mv squared over L, or the minimum speed squared equals GL. All right, now we're going to relate that to the initial kinetic energy and the change in the potential energy. So then over on the right side, we have our change in kinetic energy plus change in potential energy equals 0. So the kinetic energy final is 1/2 mv minimum squared at the top minus our initial kinetic energy 1/2 mv squared. Then the potential energy increases by mgh, where h is the total height it goes from the initial position up to the top of the circle. So notice for the ball to go from its initial position to the center of the circle, that distance is L cosine 30. Then to the top of the circle, it's another length of the string, L. So the total height is L plus L cosine 30 degrees. Multiply that by mg, and that gives us the increase in potential energy. Now we multiply through by 2 to get rid of the 1/2 and divide out the m, and I'll have v minimum squared minus v naught squared equals 2g times the quantity L plus L cosine 30. Then I replace the v minimum squared with GL. So we have a GL minus v naught squared plus 2GL times the quantity 1 plus cosine 30 degrees. Now we have a 2GL and a GL, so that gives us a 3GL. So then we solve for v naught, and we get v naught equals the square root of GL times the quantity 3 plus 2 cosine 30 degrees. So that's the minimum speed we must give the ball for it to swing all the way up through a complete circle with the string remaining straight at the top. And that finishes part B.
All right, let's look at the situation in the previous problem with the ball on the string. All right. Now, if the ball is pulled back so that the string is horizontal and then simply let go and dropped, what will be the tension in the string when it reaches the bottom? So I drew the free body diagram for the ball when it's at the bottom of the circle. So it's still moving in the circle, so we have the sum of the tension and the weight must sum to the centripetal force. So we have our centripetal acceleration is going to be up toward the center of the circle. So we have the tension up minus the weight down equals the centripetal force. Then we can use conservation of energy to relate the velocity at the bottom to the initial potential energy.
All right, let's do a variation of the previous problem. So this time we're going to pull the ball back so that the string is horizontal and then just simply let it go. What will be the tension in the string when it reaches the bottom? Well, at the bottom, the ball is still moving in a circle, so the sum of the tension and the weight must sum to the centripetal force. This is just Newton's second law. Then we can use conservation of energy to relate the velocity at the bottom to the initial potential energy. So I've drawn the free body diagram for the ball at the bottom. So we have the weight downward, the tension in the string upward. It's still moving in a circle, so we just do the sum of the forces equals ma, where a is our centripetal acceleration. So we have T minus mg equals mv squared over L. And then solve for the tension, we get mg plus mv squared over L. All right, so now we can find the tension if we know what the speed is in terms of the initial conditions. So we apply conservation of mechanical energy. The change in the kinetic energy plus the change in the potential energy equals 0. The kinetic energy is going to increase. Our initial kinetic energy, of course, is 0, so it increases by the amount of 1/2 mv squared. The potential energy decreases because we're losing a distance L in height. So the change in the potential energy is minus mgl, and then those two sum to 0. Solving for v squared, we get v squared equals 2gl. Now I can plug 2gl into v squared for the tension equation. So we have the tension equals m times 2gl divided by L plus mg. Well, the L divides out, so I have a 2mg plus an mg, and so the tension equals 3mg at the bottom. So the tension is equal to 3 times its weight when it reaches the bottom.
All right, here's a fun one. We have a child's toy consists of a loop-the-loop track and a car that can travel without friction on the track. The car is accelerated by pushing it with a constant force F over a distance d and then releasing it. The car will then travel at a constant speed until it encounters the loop of radius r. So part A, what is the speed of the car at the end of the push? Part B, what is the speed of the car at the top of the loop? And then C, what minimum distance d must the child push the car for it to stay in contact with the track through the top of the loop? So we want to make sure he can push it for a great enough distance to give it enough energy so that it can make it through the loop without falling. All right, we'll just do this step by step. And this illustrates all the different things that we've learned about work and energy. All right, so part A, what is the speed of the car at the end of the push? Well, we can apply the work-energy theorem. We're applying a force over a distance, and we know the net work is equal to the change in kinetic energy. So the force times distance equals delta K, and then knowing the kinetic energy and given the mass of the car, we can find the speed. So we have force times distance equals 1/2 mv squared. Solve for v, and we get v equals the square root of 2 F times d over m. So if we know the mass of the car, we know the applied force and the distance, then we get the velocity or the speed of the car at the end of the push. So that's the answer to part A. Now B, what is the speed of the car at the top of the loop? All right, so there's no friction involved, so we know mechanical energy will be conserved. So we know the initial kinetic energy now after the push, and then we just apply conservation of energy to find the speed at the top of the loop. So we know change in kinetic energy plus change in potential energy will equal 0. So change in kinetic plus change in potential equals 0. So our change in kinetic energy, we have the final 1/2 mv at the top squared minus our initial 1/2 mv squared, plus the potential energy is going to increase. The car is going to go up a height of 2r, so we have mg times 2r for the increase in potential energy, and then those all sum to 0. We want to know the speed at the top, so now we just solve that for the speed at the top. So solving for the speed at the top, each term has a mass, so that divides out. We multiply by 2 to get rid of the 1/2, and so we get v at the top squared equals v squared minus 2g times 2r. And that extra 2 came from multiplying by 2 to get rid of the halves. And then we get v at the top equals the square root of 2 times force times distance over m minus 4gr. So we've got the answer. Now the next part. What minimum distance must the child push for the car to stay in contact with the track through the top of the loop? All right, so we know how to solve this. First, we find out what minimum speed must it have in order to stay in contact. And we do that by applying sum of the forces equals mv squared over r. And then relate that speed to the distance that we push by applying conservation of energy. So to stay in contact with the track, the car must have enough speed. At the top of the loop, the forces on the car are the normal force on the track pushing down, and the weight of the car also down. Those two sum to the centripetal force to keep it in the circle. The minimum speed then is just when the normal force goes to 0. So then we have mg equals mv squared over r, or v at the top squared equals to gr. So this looks familiar, right? This is the same minimum speed we have to have for the ball on the string in the vertical circle to stay through the top, to stay in a circle when it goes to the top. So that same speed. Now we can relate v top squared back to the distance d. We solved that previously, so we just use that equation, but now substitute gr for the velocity at the top squared and solve for the distance d. Okay, so conservation of energy, delta k plus delta u equals 0. The delta k, we got 1/2 mv top squared minus 1/2 mv initial squared plus the increase in potential energy, which is mg times 2r, and those all sum to 0. Well, now I substitute the v at the top squared with gr. So I have a 1/2 mgr minus the force times distance. The force times distance gives us the 1/2 mv initial squared, and then plus the 2 mgr. Now I solve for the distance. So we have force times distance equals 5/2 mgr, because 2 mgr plus 1/2 mgr gives me the 5/2 mgr, and then the d equals 5 mgr over 2f. So that's the minimum distance he has to push in order for the car to have enough speed to make it through the loop.
All right, so that's the end of this video. If you have any questions about any of these problems or any comments or suggestions, please leave them below. I'll do one more video with some more examples of applying conservation of energy. So don't forget to hit the like button and subscribe. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel, and please subscribe. I hope you find my videos useful.